Okay, this is a review that I did a couple of years ago. It's been up there for a while. And it's a fairly good review, so I'm going to kind of just use this because I can get through it quickly and say everything that my people brain will allow me to say. Okay, around some of this stuff, and hopefully give you a picture of the broad sweep of the course and how things are interrelated. I do have other boards down here, so if I want to write something a little extra, I want to do it. But the less I write, the faster I go through it, and the more I can cover it. Normally, it's not the way I like to do class. But right now, for review, that's probably the best way. Okay, so vectors. We got dot product, we got cross product. We know about dot product. It's the magnitude of this times the magnitude of that times the cosine of theta. We're being the angle between the two vectors. It's very handy if you want to project a vector on another. Okay. You got the cross product. Right hand rule. First vector crossed into the second. If you switch the order, you're going to switch the cross product. Okay, you're going to get the name cross product. So it's not commutative. It's the magnitude of the cross product is the magnitude this vector times the magnitude of that vector times the sine of the angle. So when the vectors are perpendicular, sine is equal. Okay, I'm sorry, the sine is 1. Cosine is 0. Sine is 1, and your cross product is as big as it can be for vectors of that magnitude. If the vectors are parallel to one another, you're going to get a cross product. Okay, you get a zero cross product, a zero vector. Cross product is perpendicular to both of the vectors, which makes it very handy for calculating normal vectors. Using your partial derivatives, x partial times I plus k, y partial times j plus k. Take the cross product. That should all be very familiar to you. And if I say anything that isn't very familiar to you, look at the clock, write down the time, so you have some idea where to look at it. Okay. Okay, projections. Here's a picture of projection. Here's V, here's W. We're going to project V onto W. Projection goes at a right angle. So just project the tip of V down to here. And right there is the projection. Now you have a scalar projection, which is how long this side is, and also whether it's positive or negative. Then you have the vector projection, which is just a scalar projection multiplied by a unit vector in the direction of W. Really easy to get a unit vector in the direction of W. Just divide W by its magnitude. So you could easily do that, and that's all this says. Okay, so the projection on the W of V, this is a projection without an arrow. And this is the magnitude of V, which I just designate by V without an arrow, times the cosine of theta. Triangle. If you don't understand that this side is this side times the cosine of theta, go back and take trigonometry. Okay, that's got to be second nature too. Got to be okay. And I'm pretty sure everybody goes. Stuff really has to be as intuitive as possible, but also as rigorous as possible. Well, the vector projection, you just take this scalar projection and multiply it by the unit vector, which is what I just said. Okay. Well, what is V cosine theta? Well, what we mean is the magnitude of V times the cosine of theta. The dot product of V and W is magnitude of V times the magnitude of W times the cosine of theta. Okay, if you want the magnitude of V, just divide both sides by this. Okay, and that's what you do. Okay, so the scalar projection is just V dot W, which is this. Okay. Here's your V, here's your cosine theta. You divide by the magnitude of W. That's it. Okay. In other words, your V cosine theta is V dot W divided by negative W precise. And that should be straightforward, that should be pretty obvious. Okay, if you can't figure that out by yourself, if you have to get the formulas. That's where you can. Okay. The vector projection, there is an arrow over that, but that's going to go. So or the two values smudge. Okay. Projection on W of V then is just a scalar projection, which is there right here, times the unit vector. Now you just rolls that all into one formula and gives you a magnitude of W squared, which obscures the meaning. I don't like to obscure the meaning, it doesn't hurt to write that out. If you use magnitude of W squared without understanding why the W magnitude of W squared, you're not understanding the projection, you're not understanding what you just did. Okay. Now, if you understand it, it's fine to write that out. So, okay, I know that's magnitude W over magnitude of W multiplied by this with a magnitude of W. So I'm just going to write the square of W. Okay. Now, if you get it right, okay. I'm just saying rely on deeper understanding than just a memorized formula. Because there's a strong tendency when you memorize a bunch of formulas, get them mixed up and use the wrong one. You want to understand it as deeply as possible. And that's what you want to focus on. That's gotta be the goal. As best you can. I mean, you know, everybody gets into the test, you've got a combination of things that you understand pretty deeply and understand pretty well, things you're a little fuzzy on, you think about the formulas. Okay, no way to make an A, but it's probably a way to make a B or C. Okay. Nothing to get by, hopefully. Okay, so anyway, let's go to planes. It's also weakness on the idea of planes. It's a simple idea. A plane through X naught, Y naught, V naught, perpendicular to some vector n, which will be our naught vector. Okay. Point X, Y, Z is on the plane. If and only if this vector, the vector from X naught, Y naught, Z naught to X, Y, Z, which is here, X minus X naught I, X minus C naught K, is perpendicular to M. Okay. And that means it is dot product with any zeros. So that's the equation of line. Now that gives you, you know, if n is AI plus BJ plus CK, that gives you your A times quantity X minus X naught plus B times quantity Y minus Y naught plus C times the quantity Z minus C naught equals 0. You take your constants, put them over the other side, you got a standard equation of the plane. That's also why if you have the equation of a plane, some multiple AI plus BJ plus CK for some constant, your normal vector AX plus BY plus CZ equals some constant. Okay, then your normal vector is AI plus BJ plus CK, just for the same reason. It's an equivalence. You want to understand that you want to have that picture. And this is a good time for me to draw a picture that just got done in calculus classes, emphasizing you got to put things in the graph and get the picture to understand it. Don't just memorize a bunch of formulas and methods and do the arithmetic. You don't understand it. You do that. Some people maybe do. But for the most part, that's not good strategy. Okay, so here, the picture here is X naught, Y naught, C naught. And X, Y, Z. This vector. This vector. Dot product. Is 0. So. AX plus BY plus CZ equals D. For D is AX naught plus BY naught plus CZ naught. If you have this, or the equation to put in this form, you just read off a normal thing. You want to use normal divided by small. Okay. So you really want that picture. Now, and again, I don't see evidence of people thinking that much in terms of that picture, or in terms of the formula. The picture makes sense of the formula, it makes it easy to make the formula. Okay, line through X naught, Y naught, Z naught, parallel to B. Now, when I look at that, what we got a magnitude of B there, there's no magnitude sign on the other side, right? So, but if you look at what I was doing, so okay, that's a parallel. Okay. X minus X naught I plus Y minus Y naught J plus Z minus Z naught K is a vector from X naught, Y naught, Z naught to X naught, same vector we just read there. And now this is 2 points, and this has to be parallel to B. Well, it simply means that this vector is some multiple of B. Right, there's our parameterization. Okay. And T, it's a line. Okay. I could down a little bit. I hate to have the exception, but I'll do it anyway. Okay, minus infinity. Infinity. No matter how small or how big this vector is, these multiples are going to give you points of 1. Okay. That picture should also be obvious. See the picture of toast. Every toast is ever been written. It's a little bit wrong picture. Okay. Okay. Okay, well. Now, a path in space is defined, can be defined by an arc to the this is something you're pretty much used to because you've been doing a lot of stuff with paths in space. I'm not sure you understand it. Okay. Just some function of t times I plus function of t times j plus a function of t times k. That those functions will be x of t, y of t, z of t. Okay. Then we do the derivative. Okay. Well, you can easily put the derivative. If you've got a well-behaved function, is tangent. Curve. Okay. In other words, if x, y, and z are all smooth functions, you're going to have a smooth curve. Have a derivative at every point, and the derivative is always going to be tangent to the curve. And we use that. We use that when we parameterize a curve to do an integral function with the theorem. Already? Fine. I'll play with the curve, whichever. All right. So R prime is in the direction of motion. Now we can think of this in terms of motion. He doesn't have to be interpreted as time. It could just be a parameter. It could be U or V. S. Right? In any case, though, R prime is going to be the rate at which your position changes with respect to that parameter. That's something we haven't emphasized as strongly as I might like to. Okay. Kind of try to lock in on that statement. It's on 101 right now. Started this video about that's an important statement. I'll say it's more whatever your interpretation of your parameter is, you don't have an interpretation. This is the rate of change of position with respect to that parameter. So if you multiply that rate of change by changing the parameter, like R prime of U times delta U tells you how far you go in that delta U, approximately how far you go in that delta U interval. Do that at a sample point, it gives you an increment of R points. Okay. This was an example. Okay, well, a little bit more about motion, though, because we do want motion interpretation. This is a unit tangent vector. You just divide the vector in the direction of motion by its magnitude. It's still tangent because it's still got the same direction. It's now a unit vector. Well, unit tangent is a good thing. P prime is normal. Okay, that's because the unit tangent vector. Okay. Here's your unit tangent vector at one time. Here's your unit tangent vector at another time. So you've got a unit tangent vector that goes from here. Right there. They're both unit vectors, so these vectors form an isosceles prime. The change, you know, the unit tangent vector is a vector from here to here. Okay. The vector in the limit has your interval brings to zero as your delta U, if it's a U interval, swings to zero, is going to be perpendicular because this is my isosceles triangle being unit here, unit here. That means that these two angles have to be equal. Well, this angle plus this angle plus this angle add up to 180 degrees. As this angle shrinks to zero, we end up with two angles that add up to 180. So we approach two angles, two equal angles that add up to 180 degrees. That's why the unit tangent vector is the derivative of the unit tangent vector is perpendicular. Okay, now the derivative of the unit tangent vector is this. We just divide if small t is your parameter, which is what I have in the box that we use. Small t is your parameter. You take the delta limiting value of the change in the unit tangent vector, this thing, divided by the time rate. Or the t is regard to as a general parameter. Okay. Well, both of these are going to approach zero. As t approaches delta t approaches zero. So is the length of this vector, but in the limit, you have what approaches a constant ratio. And hopefully you understand the limits of the derivatives in a way that makes sense for what I just said. Okay. So I'm limiting value, you have a delta t, which is the rate of change of the unit tangent vector, which is perpendicular to the unit tangent vector, therefore normal. So here's your delta t over delta t, delta big T over delta little t is very close to perpendicular in these vectors. If delta t is very small. Okay. Now, if you want a unit normal, you calculate t prime and divide by the magnitude of t prime. That gets to be a pretty long calculation. If you haven't done it, good for yourself. Okay. I did it several times. I had a lot of time in this. Probably would have done this more times, but I just wanted to make sure my algebra was strong. It's got to be pretty strong to get that right. At least confident. Okay. Okay, well then, our double prime your acceleration if t is time. So acceleration is a second derivative position. What's our double prime? Well, it's like our prime is X prime I plus Y prime K plus C prime K. Our double prime would be X double prime I plus Y double prime K plus C double prime K. Prime being your derivative with respect to the prime. Okay. And another way of looking at this too, and it's gonna come up somewhere. I think it does. We're saying. When you like this, that's all fine. Okay. Pretty obvious, right? Our prime is magnitude what you need to. Okay. Delta S is magnitude of R prime times delta T equals square root times delta T. So your arc length is going to be the integral. T1 to T2 of the square root times delta T. Okay. If you want your mass, you have a mass density function of position. You multiply the mass times your length, the mass density times the length. And partition everything against sample mass density, mass density times the length, gives you the mass in that delta T interval. You just kind of throw in your mass density function here, and your interval then gives you the mass. Okay. Important idea. And there's a lot, it can build quite a bit of that idea. And hopefully did when you did the homework. Okay. Presentation's okay, it's a good place to start. You want to go fast. Okay. Okay, well, back to this. Got your acceleration back. Okay. So you're moving along this curve. At any given instant, you're moving in some direction. And you have some acceleration. Okay. You have forward acceleration in whatever direction you the tangent is. So you're speeding up. But you also are typically on the curves, you have a centripetal acceleration perpendicular. So you have parallel and perpendicular components of your velocity. That's important for the modeling stuff that's moving. Okay. I got some really pretty neat videos. I don't really want to read on the rides at the carnival is set up at the back of this one. Okay. It's still called the back of this what used to be. But anyhow, in September, you get some pretty neat videos, just a little carnival stuff. So you know, you've got these things that are parts that are going around this way, and then this thing's tilting and doing all that stuff. You know what I'm talking about. Your parents, you're old enough to go on those rides and watch. Okay. You get some interesting motion. Okay. You can model it all with this. And you got this thing moving about on the axis. So you're temporarily in a circular pattern. This thing's spinning about another axis. Okay. You just superimpose all that. And you get a function. You get an RT function for any of those rides. Okay. Yeah, at least you get a good model. Yeah. Start conjecturing what it's going to feel like to be on that ride. Okay. Greater your centripetal acceleration, the more you push back in your seat. Okay. Of course, you're also speeding up, but they usually don't speed up that fast. So you don't feel that so much. What you really feel is a lot of centrifugal acceleration. Kind of think about that anyhow. Your speeding up is in the direction you happen to be moving at that instant. And the centrifugal acceleration is how fast you get a tangent vector. Okay. It's a great change in that tangent vector. Calculate those components, what it was R double prime acceleration, project R double prime on T. That's the acceleration component in the direction of motion. Right? That's a tangential component of R double prime, which is again how fast you're speeding up or slowing down. R double prime minus that projection is the normal component. Why is that? Here's a picture. You've got your R double prime in this direction. The blue represents what might be your unit tangent vector. Same direction as R double prime, that you divided R double prime by its magnitude. So you got that. And here is your R double prime. It's got a component in the direction of motion. Okay, direction of the unit tangent vector. And it's got a component perpendicular. That component is your centrifugal acceleration. That component is your tangential acceleration. And if you've got the well, this is the tangential acceleration on the scale of your double prime vector. If you subtract this vector, if you vector back this way, right there it is. Okay, this is labeled as negative R double prime parallel. Okay. Getting confused by my parallels, my double primes. Focus my eyes on what I need to focus on. Again, from here to here is your R double prime, the projection of R double prime parallel, the projection of R double prime in the direction parallel. We should understand that. If you do negative R double prime parallel, added to R double prime, you get R double prime perpendicular. It's your R double prime minus your R double prime parallel. That's a picture you want to be able to draw. Need it. Picture you want to understand. Tells you pretty much everything you need to know about the parallel and perpendicular components of your acceleration, which are very relevant to motion. And too much acceleration, you die. Okay, too much centrifugal acceleration, or too much along the straight line acceleration. And if you're designing one of those mechanisms, you're going to want to model that. You're going to want to say, okay, if I do this and do that, and speed the thing up to this, what's the maximum acceleration we're going to get? If it exceeds 2 G's plus acceleration of gravity, we could get in trouble. Somebody could pass out. Okay. Yeah. Very practical purpose, especially in mechanical engineering. It's real important. You also have the oscillating circle, and I didn't do much with it. We're not going to do much with it today because your homework really didn't cover it, and that's just part of the thinness of the web assignment. So it's okay, it's solid. But, there we go. Yeah. Now the oscillating circle is just a circle in the plane that's parallel to both your velocity and your acceleration. Okay. And its radius is such that it matches the curvature. So it's a circle that just fits right into the cup of the curvature. And it's not difficult to come up with the formula for that. But it's another step. It's interesting and it's worth looking at. But sometime after the course is over, it's not going to be an exam. Okay. It's an interesting thing. It really should be part of the course, but it's quite neat. Okay. Okay. Binormal is perpendicular to the plane of motion. Okay. The binormal is just the cross product of your unit tangent and unit normal vectors, which are easy to calculate. Messy. When I say easy, algebra is a bit challenging, not too bad. Okay. But it can be calculated. It's an easy process to calculate it. This an error prone. Okay, anyway, we call this the binormal vector. So you got your unit tangent, you're moving along this curve here in this direction. And your unit normal is in this direction. It takes the cross product and that normal to the unit tangent and unit normal. So now you've got a three-dimensional coordinate system that you're carrying along with you. It keeps changing. Okay, like if the curve goes like this, you're reading binormal, okay, we can do it on. Okay. You keep changing the plane in which you're moving. You don't have to keep changing the plane, but those rides are going to change the plane. The whole thing going around with the seat that's rotating here and then plane is changing. Yeah, you can keep moving at a different plane. Okay. If you find an airplane, plane of motion is changing, as you go up, as you go down, as you bang, all that stuff. So that's kind of a neat idea. So you have this picture. I'll go ahead and have it. You got it. The tangent. With the coordinate system at this instant. If you're doing this sort of thing, binormal. That binormal is a unit vector of T and a unit vector of T is going to be fine. And so you've got like an IJ thing, temporary, instantaneously temporary set of unit vectors. Okay. Well, that's motion. That's vector. That's okay. It's not on motion. Arc lengths, it's not on the function. Okay. Quadratic surfaces. I think this notch quadratic surface is here's a quadratic formula. Okay. It's an ax squared plus bx. And a cy squared plus by, and an ec squared plus xc. And then plus some constant. That's the general quadratic form. There's nothing else you can add back to this in the form of what those terms. And have it still remain. Okay. A set that equal to 0. And it then is the equation of a quadratic surface. Okay. And it can be put in the form of a times x minus h squared plus b times y minus a squared plus c times c minus b squared. Okay. Equals constant. Just by completing the square on the ax plus bx, c minus easy square plus x. Then you know how to translate the thing you do to quadratic surface centered to the origin. It's not really centered with quadratic surface. But is in some sense symmetric. Some of the actions. It's like the Potter form that we studied, just transferred over, shifted X units in the X direction, K and Y, P and C. She's always pointed and surface is what's pointed. Okay, well. If these are equal, all equal to zero, then A, C, and D are all non-zero, then well, then we essentially have AX squared plus CY squared plus ZZ squared equals zero. Because H, K, and B are all zero. And okay, well, the equal zero is so, yeah, it could be equal to constant. But anyhow, if A, C, and D are all positive, then we can't be which. Let's Z equal constant, we have AX squared plus CY squared equal to constant, right? And that really actually left zero. So if Z is zero, we got AX squared plus CY squared equal to G. So that A over G X squared plus C over G Y squared equals 1. And now you're pretty much in the form of the ellipse, okay? Another step, put the A over G into the denominator, so it's X squared over G over A, but that's just the detail. The overview is that if these things are all positive and G is greater than zero, then you have an ellipse. Okay, if A, C, and E are all positive and G is negative, got nothing. Because if these are all positive, then multiplying by squares, everything's going to stay positive. Can't have a negative. All right. Okay, so otherwise, if A, C, and E are not all greater than zero, how are you going to have hyperbola? Okay. Again, assuming that A, C, and E are all non-zero. But those are the only two choices that A, C, and E are non-zero. In any case, the intersection with the coordinate plane is a given coordinate plane. It's either an ellipse or hyperbola. And there's a picture of how you graph an ellipse and hyperbola. I mean, you do that. I'm not going to go into the details of that. It's just pretty simple, which I gave you earlier in course. I'm going to take this too far. Just an overview of the review. Want to actually do this next time after you review a little bit. Probably will. Okay, anyhow, this is just a reminder of how to graph ellipses and hyperbolas. And you got to know how to do that. All right, now get the arc length and curvature. If you got a function of more than one variable, then see, because Fy has a three-dimensional graph. I mean, it's a surface in 3 dimensions. Okay. It's a single value, so if it's above any xy, there's a single value. If we let y be constant, then, oh, that's in blue. Where's the plane where y is constant? Thank you. And we're not doing our plans for a track with having parentheses. I thought that's what I've gone with it. That's all. What we're doing here, we're cutting this surface with a plane y is constant, parallel to the x, then we get the curve. Okay. We cut it parallel to the y plane for actually it was constant. Then we get another one. Well, this curve, blue curve, has a tangent vector at this point. The X and Y. The X equals constant plane and the Y equals constant plane. Each of these curves has a tangent vector. Okay. Now, those tangent vectors are familiar. I equals partial vector respect to A in our J plus partial vector respect to Y times. Okay. And you need to understand why that works and how that works. It's just the slope of each of these tangent lines in that plane is equal to the derivative. And in the X equals constant, and that's Y that's varying, and Z. Okay. So the slope is the change in Z divided by the change in Y. If the change in Y is 1, then change vector, and the associated change in Z is in the partial vector respect to Y, because that's the rate at which this value is changing with respect to Y. Okay. So we did a lot of hand waving and I cut out those blocks. You really need to understand those blocks. You understand all integrals in terms of those blocks. You need to understand the tangent vectors, the normal vectors. In terms of the blocks, the cross products that I'm looking at here, which is the slope occurs this way to this end of the block, and this way. You take the cross product, there's your normal vector. So we've done a lot of that. We want to relate this. We want to really lock this whole idea and very, very tangible. Let me say tangible. Okay. So that's what we're doing. That's the picture. And that's the picture that gives you tangent. These vectors are in your tangent plane. And it's a cross product. Now, normal new tangent plane. You've got this point that you have before. This is a I could call that a small line on it. But this is the general XY point. This is how you get two vectors in the tangent plane, the cross product into the Y, and what you have the normal and the point in three-dimensional space. Right out to the equation of the plane. Okay. Okay, well. Okay, so I fleshed out a little bit here. There's your normal vector. Near XY, L of XY, your tangent plane. Structure makes sense, doesn't make a lot of sense. But okay, your tangent plane is through X, Y, F of X, Y. With the little coordinates. The normal M. So you can easily write out the equation of the tangent plane. And near this point, if you have a smooth function, you've got the tangent plane is going to give you a good approximation to the actual value of the function. It's like a tangent line on a single curve gives you a pretty good approximation if you step close enough. You get the value. Okay. And then I'd say this is a differential approximation that you really want to leave here with a good idea, a good concept of differential approximations. Something that I don't see much of coming out of calculus. Okay. But good bit about it. No. do differential approximations in one variable. Look up the differential approximation. I would understand this as a generalization of the differential approximation of one variable. It's just a tangent line approximation. This is a tangent plane approximation. Okay. The directional derivative in the direction of u. Okay, so I went back and figure this picture. If the rate at which the value of the function on this surface whatever it is changes if we move in this direction, the rate with respect to how far we move in this direction. Right. It turns out that that's just fx cosine theta plus fy sine theta, where theta is the angle of u with the positive x direction. I really want to understand why that's the case. Like there's too much to make that specific. I might try to get some little bit more of this stuff. Okay, that's what it is. Okay. And it just comes down to this. Fx is 7. That means for every unit we travel in the x direction, this thing is going to change by 7. Okay. And if y is -3, what do you mean go down 3 for every 3 direction? Now, if I go at some angle with the x direction, okay, well, that vector has this component in the x direction, that would be u cosine theta. Okay. In this direction, it would be whatever my distance is here as a sine theta. And you just put all that together and you get your direction of drift. So, for example, if I'm moving at 30 degrees, okay, then how far do I actually move in the x direction per unit? Okay, so I move distance W at 30 degrees to the x direction. Then I move square root of 3/2 W in the x direction. Well, that's how much do I change? I change by the square root of 3/2 W times my fx. Times my 7. Okay, that's about 0.87. Okay. So I move distance 0.7 u in the x direction. How much does it change? For every unit I move in the x direction, it changes by 7. So it's going to be 7 times 0.87 u, which is a cosine of theta times 0.7. You do the same thing with sine of theta, and I'm waving my hands a lot. In terms of the written how that's going to take the time. Okay. And plus we, you know, I think we do that. All right, well, gradient of f is the direction maximum increase. Okay. Yeah. Trying to read my sentence. Del f is the direction of maximum increase, and the magnitude of del f is the rate of maximum increase. Okay. The directional derivative is this del f, like taking the same idea. Okay. You understand this is about difficult to understand. Del f is your partial with respect to x in the x direction. You adopt that with u, you multiply it by u times cosine theta, which is just what we do. You want me to write it out? And the same thing with the fy times sine. So if magnitude of u is 1, in this case, If you get the direction here, you has to be in the so U is cosine beta I plus sine theta j. So you're gonna end up when you do the dot product of fx times cosine theta plus fy minus sine theta, which is the direction. Okay, so it all hangs together. I didn't say that real clearly, but it's really right now. So if you want to do some like this, I want to talk a little bit more. A little bit about what's in this. So let me grab it. Okay. So. All right, here, conservative field is a field that's gradient on a scalar field. Okay. I'll also comment, we haven't really talked that much about it, especially relevant to the physics, but it's important here too. A rotational field, a magnetic field, for example, has what's called a vector potential. Okay. It's kind of making it this, especially because we electrical engineering or anything with hydrodynamics. Just like a conservative vector field is a gradient of a scalar function. Okay. A rotational field is the curl of a vector function. Okay. So your magnetic field is the curl of some other vector. Your scientists haven't done much with it. It's kind of fun to do it. But it's a pretty difficult topic. I just mentioned it. You might want to look at vector potentials. Just the analogy here, but this isn't anymore a vector, but a scalar. It's a vector, and it's a cross product. And you can prove things. Some things are pretty easy to prove. I'm not going to. Okay, now field is conservative, if and only if that's an example. Never go around that closed curve of f dot ds is 0. And the interval on a closed curve of f dot ds, yeah, it goes back to what I might have written. Remember, when you do any line integral, you do a dot, which s. Okay. Partition, and this on the point, and you're always doing something behind the delta f. And we know how to do these integrals because that's what we do. Parameterize f. If f is conservative, it's easy to prove that curl of f is 0. Because the curl of del f is del cross del f. And if you just write out, well, del f is fx I plus fyj plus fzk. Write out your determinant definition of cross product or use distributive law. And write out what it is. You would have your ijk, you have your functions, fx functions, y functions, to z, and your fx, fy, fz, and your three rows. And then just write out what you get, and everything matches up and goes to 0. Then cancel that. It's really pretty simple, doesn't take long to write it out. So, and I've indicated that, I'm not sure I wrote it all out fast. So that's something I really ought to be able to prove. And I would ask him on because it's a case. But del cause del f is always so. And it's really just a matter of writing it out. I'm not guaranteeing to be on there. I don't know what the probability is. Let's see. And I even say what I just said. Okay, I guess I should read ahead so I don't keep repeating myself. But del cross fx I plus fy plus zk equals 0. Just write it out. You can write it out. You can do it 2 minutes. Know that that's how you prove it. And probably ought to take too much minutes. Okay. Just in case it shows up. Or something similar. Okay, to do a line integral, you parameterize your path. You partition. Look at the I interval. The I minus one. Less than two, less than the I. And sample point the I star. Get your R prime of Ti star multiplied by your delta Ti. That's how far you move. As you delta S. Delta Si. Add them all up to get approximate arc length, take the limit to get the integral. Gives you the arc length. So once you've written out the sum, it becomes pretty easy to write out the integrals, because you just have to know what to do it a few times. Hopefully you've done that. So, you know, and I've already said this, but R prime Ti is X prime Y plus Y prime J plus Z prime K. So the magnitude of R Ti is X prime squared plus Y prime squared plus Z prime squared. So your R distance is this, which is this, and I actually wrote it out before. I think I used T1 and T2 instead of T2. Okay. So that's worth pointing out to us. All right. So your integral depth dot ds. The I interval you have this, delta S this times delta Ti. And it's what am I doing? Nice stuff. Looks like right now it looks like I'm just getting what I just said. That's how I do. So you got F of Ti star dot delta S. Okay, so yeah, you're trying to do an interval of F dot ds. Under the ith interval, F of Ti star is your approximation of the function to the vector function. You dot that with the delta S. Delta S being a vector now, of my change component, not just the magnitude. That gives you, okay, if your F function is Fi plus G, J plus HK, you know, F being a function T, G, and A in functions. You dot that with this. So this is just stabilizing sum of what you get. And of course, what you get when you take the dot product is that that's 5 plus G times Y times 6 times Z times delta T. And something that would actually give the dot product. Now, the only difference what I wrote here is F is going to be a function of X, T, Y, T, Z, T. You know, F is going to be given to me. This F is a function of where you are in space, X, Y, Z. This is a function of X, Y, Z. This is a function of X, Y, Z. We parameterized everything in terms of T, so I've got to write that as F of X of T, Y to Z of T. I want to write it out completely on the top. So Fi is really F is a function of X, Y, Z. X, Y, and Z are parameterized in terms of T, by X of T, Y, Z of T. There it is. And then same thing here, same thing here. And we got that with X prime of Ti plus Y prime of Tj plus Z prime of Tk. If we have our parameterization, and we know our function F, and we know all this stuff, and we divide it out. So this is looks like kind of a handful, but it's just there expand and make it flexible. Again, Find your answer in that, you can find out. It's fine. Okay. We have. So. If you have all that, write all this out, it's just gonna come out some function of T. YouTube. If we got product, we can put a lot of that. Okay. Coordinate systems. You have your coordinate systems, your volume increments, rectangular coordinates, your area increment could be like delta x, delta y. Bottom increment would be delta x, delta y, delta b, that's. Okay, cylindrical coordinates, just like polar coordinates. Well, I've got this picture here to explain what happens to the cylinder. But your polar coordinates, your area increment is your r delta theta. R delta theta being the arc, the length of this arc here. The bigger r is, the bigger this arc is. Your theta increment is expanded. Okay. So you do your r times delta theta, your ri star delta theta. Okay. That's what gives you this arc distance. This dimension. And here you just have your delta r, not just like a concentric circle. Simply defined as the delta r. Okay. The approximate area of this thing, if you let delta theta and delta r approach zero, then there's no significant difference between this length and this length. And also, if delta theta is small, this becomes nearly a straight line, so you have nearly a rectangle. The dimensions ri star delta theta by delta r. That's why you have r delta theta. R delta r. And your delta v is the 100 coordinates. Well, here you have this, now you have some delta z up here. You can use approximate. Okay. And just multiply by the area, that you have the two dimensions. Spherical coordinates. I don't have a good picture of this. Well, if you want me to draw one, that's kind of the plan too. But you don't have that. Your delta v is rho squared sine pi. It's because rho is out here. It's like r, if rho increases by delta rho, then your increments can increase by rho. Now the really need the door, you want the things in mind. So you can ask. Then I just make a note. Rectangular coordinates, rectangular solids are easy to describe. Cylinders and spheres are not too hard. Okay, just not how to do that. Cylindrical coordinates, cylinders are easy, spheres are a little harder, cones are pretty easy. Cylindrical coordinates. Rectangular solids are not that easy, but it's worth the exercise to try to do it. End up a lot of hard to describe. Spherical coordinates, spheres, ice cream cones. Okay. Ice cream is great. And you should understand pretty well. Moment intervals. The first moment increment is ri star delta ai. What's that? Well, you got some area out here at some distance r from the axis of rotation. And your first moment is just r times that. Okay. And it's like a torque. Second moment is like the moment of inertia. If you don't have physics, I don't surely have those concepts. Okay. So it's 151. stop there, pick it up next time, and come in with questions if you have them. Things you'd like me to say a little more about, and we'll see what we can do.